Hi, my name is Amy Ferrer, and today I will be introducing the topic of isoquants, the different kinds of isoquants, the properties they possess, and will show the graphical representations of each. I will begin by going over the different kinds of isoquants that exist depending on the types of inputs a firm has available to them, so let's begin. In the scope of this presentation, we will be discussing two basic categories of inputs, namely labor and capital. They are important to highlight since output function isoquant curves are lines that connect all combinations of labor and capital that lead to an identical output. So in economics, we know that firms will generally maximize output by utilizing all of its inputs for maximizing production of the goods and services that they can sell for a positive price. They are analogous to indifference curves for utility functions. And just like indifference curves, there are an infinite number of isoquants for every production function. So moving along an isoquant curve shows the substitutability of labor, represented by the capital letter L, and capital, represented by the capital letter K, for that particular level of production. So to draw one, we can start by arbitrarily choosing an output level, represented by the capital letter Q, and then finding all of the combinations of labor and capital that the firm could possibly use to produce this quantity, meaning that Q, output, is constant. So this means that every single point on that curve represents the same level of output. Depending on the kinds of inputs that a firm has, production functions can produce different kinds of isoquant curves on a graph. So a firm can have perfect substitute inputs, which will yield a production function graph whose isoquants will be straight lines. Perfect complement inputs, which will lead to a production function graph whose isoquants will be right angles. And finally, we have Cobb-Douglas production functions, which will have isoquant curves that are smoothly curved, bowed in, and convex to the origin. The first type of isoquant substitutes one input for another in a fixed ratio and are called perfect substitute production functions. Isoquants for perfect substitute production functions are therefore straight lines. The isoquant lines in the production function graph will have a slope, also known as the marginal rate of technical substitution, of -1, which will all be parallel and negatively sloped. A real-world example of this that helps visualize the reason why these are straight lines of perfect substitutes is when two inputs can be swapped in a fixed ratio to produce the same output. So, for example, a pastry shop can produce a no-bake pastry using the help of either a little pastry contraption or two human workers. They will both produce the same level of output and can be directly substituted for one another. The next kind of production function is for perfect complements, which will yield right angle isoquants whose inputs are substitutable in fixed proportions. So production will only increase in a perfect complement production function when both inputs are increased, since only increasing one or the other will still mean that output is tethered to whichever input is the limiting factor. So in other words, output is dependent on the lower quantity of the two inputs, hence the min in the perfect complement production function, which looks like this. You can see on the slide. Each right angle curve in this graph represents isoquants. So the vertical portion of each curve has a marginal rate of technical substitution, or the slope, or MRTS, of infinity, while the horizontal portion of each curve has a MRTS, marginal rate of technical substitution, of 0. And the corners of these curves, you will notice, will lie on a line, where all of the points display the correct ratio of inputs. So a good way of visualizing these curves in a real-world application is to think about the interaction between two inputs that need one another to produce something. So an example of this in the real world would be a machine operator and a machine, both of which depend on one another in a fixed proportion to produce output. So the machine cannot operate without the operator, and likewise the opposite is also true, where the operator cannot produce any additional output without the machine. So for example, a food prep worker at a restaurant that uses a chef's knife to cut vegetables will not benefit or be able to produce any more work by acquiring more knives. And on the other hand, adding more workers when there is only one knife will not produce any additional output. So that's the case of perfect complements, where more of both inputs are required to produce more output. So now we will go over Cobb-Douglas production functions. And this might seem like a familiar term because it can be easily confused with Cobb-Douglas utility functions, but they are not all the same. Where Cobb-Douglas utility functions deal with optimal bundles of goods a consumer has to choose from to achieve the same level of satisfaction, which lie on the same indifference curves, Cobb-Douglas production functions have to do with the optimal combination of inputs for maximum production at the lowest cost to the firm, represented by isoquant curves, namely labor and capital. Cobb-Douglas utility functions are used when dealing with a mix of inputs that have variable substitutability, where they are neither perfect substitutes nor perfect complements. The general form of a Cobb-Douglas production function looks like this, where A represents overall productivity, so as A increases, the same number of inputs yields more output, and the alpha and beta parameters represent the contribution to the output of each input. So just like other production functions, in the case of perfect substitutes or perfect complements, there exists an unlimited number of isoquants depending on whatever level of output a firm chooses to produce. So note that the slope of each isoquant is, again, the marginal rate of technical substitution, MRTS. The marginal rate of technical substitution describes how much you must increase one input if you decrease the other input by 1 unit in order to produce the same output. So the MRTS is simply the ratio of marginal product of labor to marginal product of capital. And the marginal product of any input just tells us how much extra output will result from a 1 unit increase in the input. Additionally, MRTS tells you how many units of capital you would need to add, which is the rise of the curve, if the labor decreases by 1 unit, which is the run of the curve, to maintain the same level of output. Or in other words, to stay on the same isoquant curve. So this makes intuitive sense, being that increasing or decreasing labor will mean that capital will need to be increased or decreased, and MRTS is telling of the ratio of which that will occur to maintain the same level of output. So that means that any combination of labor and capital inputs that result in a higher or lower level of input will lie on a different isoquant curve. That's why the MRTS will be the absolute value of the slope of any isoquant curve. So of course, it is important to note that Cobb-Douglas production function isoquants have defining characteristics that they all share. Firstly, isoquants that present greater outputs are further from the origin, which makes sense because since they require greater amounts of each input, of course they will be getting further and further away from the origin. They also must never cross, because if they did, intersecting isoquants will represent the same level of output at some point, which would go against the entire purpose of isoquants, and they would also not be consistent with each isoquant's specific ratio of inputs. Additionally, isoquants are also downward sloping because there must exist a trade-off between inputs as one is substitute for another. Lastly, isoquants do not bow out because they demonstrate the fact that firms will always pursue the maximal output that can be achieved by using a mix of inputs. In conclusion, isoquants provide a powerful visual representation of how inputs can be substituted in production, with their shapes reflecting the underlying nature and relationship between inputs that a firm has available to them. Perfect substitutes yield straight line isoquants, perfect complements form right angles, and Cobb-Douglas production functions, of course, produce smooth convex curves, each illustrating different degrees of input substitutability. Understanding these distinctions helps firms make efficient input decisions tailored to their specific production capabilities. Thank you, and I hope to have provided a better understanding of isoquant curves.